filling in the notes. This follows straight on from the flood fill, bottom of page 87. So we looked at the flood fill on Monday. Essentially, the flood fill, you pick a pixel somewhere in the middle of a polygon, and if you've drawn the outline of your polygon, so you've already used either Bresham's algorithm or one of the circle drawing algorithms to draw an enclosed shape, you pick a pixel somewhere in the middle of that area, and what it will do is it will fill the area with filled pixels. Okay, so that's flood fill, so it kind of floods out from an interior pixel. Scanline filling is totally different. Scanline filling only works for polygons. So, and what it does is it draws the whole polygon in one go. So it doesn't need the outline. Now, the scanline filling is much more useful to us in graphics than flood fill. Flood fill is only really useful in drawing packages. Scanline fillings is how we draw polygons, so how they're drawn on the screen. And we're also going to use this when we look at texture mapping. So in a couple of weeks, we're going to be looking at how we apply what we call texture mapping. This also uses scanline filling. Okay, so a couple of terms which we're going to be looking at. A scanline, I'll be using these terms quite a bit over the next few weeks. A scanline is simply a horizontal row of pixels. Okay, so with scanline filling, we always deal with pixels row by row. So we start at the top, or your top of your screen, and each row of pixel is a scanline. And when a screen is actually, this applies to your phone, your TV, your computer monitor, what it actually does is it goes from the top to the bottom, and it goes back to the top again. So if you get a high-speed camera and actually record a TV screen or something, you'll see sort of some weird sort of strobing effects where you get horizontal lines going down. That's because on a display, you actually render the top line first and you go down, so horizontal rows. That's what a scanline is. And what a scanline algorithm does is it loops through rows of pixels starting at the top of the polygon. Okay, so if you've got a polygon to fill or to render, you start at the highest point on that polygon, and that's where you start. And you look at horizontal rows across the polygon. Now, where the edges of the polygon intersect with the scanline, so scanlines are horizontal. Okay, so you might have some horizontal line defined by the scanline will intersect somewhere on the edges of the polygon. Those points are what we call scan extrema, because the point where the polygon edges intersect with the scanline are going to be the outside of the polygon. If an edge intersects with a scanline, we calculate the x-coordinate of the scan extrema using linear interpolation. So we just interpolate between the vertices of that edge. Once we've got all of our scan extrema for the current scanline, we sort them into ascending order. Okay, so I'm going to be looking at a couple of examples in a minute. So once we have the x-coordinates, we sort them in ascending order, and then we fill in all of those pixels between pairs of scan extrema in the sorted list. Okay, so scanline filling, essentially scanline is a horizontal row. Where the scanline intersects with the edges of the polygon, we call them scan extrema. We calculate those using linear interpolation, and then we fill in between. So every pixel between two scan extrema are filled in. Okay, so this is the algorithm. Okay, so what we get is we just define a set of vertices. Now this comes from, I mean, we've been working with sort of, you know, with your virtual world, your village. So you have poly array, you have the vertex array, etc. So we just start with a set of vertices v1 to vn. And also we need the color of the polygon, which is what we're going to fill it in. What we do to start with is for each edge in the polygon, we calculate the change in the x-coordinate between the vertices divided by the change in the y coordinate between the vertices. And I'll explain why in a minute. So because edges of the polygon are straight lines, okay, essentially this is 1 over the gradient of each line. So once you've done that, for all scan lines in the polygon, so you start at the highest point on the polygon and you go down by 1 each time, and you end up at the lowest point in the polygon. So your y coordinate starts off with whatever the maximum y coordinate of your polygon is. You calculate your x values, okay, and that's your first scan line. The next y coordinate is simply y minus 1, because you're going down the level. Then you calculate the scan extrema, so where that scan line intersects the edges. Okay, and you do this for all scan lines, for all edges. So you loop through your scan line. Okay, that's taking each line in turn. So let's say we just got 1 line. We have to loop through each edges of the polygon. Okay, so if you've got a 4-sided polygon, you've got to check 4 edges. Now, you do a little if statement. If the edge intersects with the scan line, sometimes it will, sometimes it won't. So that's why we need that little bit of logic there. If the edge intersects with the scan line, we calculate the x coordinate and store it in some array. Okay, so once you finish this loop for all the polygon edges, you'll have a list of x coordinates. You sort that list into ascending order, and then you take each pair of coordinates. Okay, so let's say the first 2. You take those first 2 and illuminate all the pixels between those 2. Then you take the second pair, so that'll be 3 and 4, and etc. Okay, so that's the algorithm. I'm going to show you it by use of this example. Now, this is the same polygon we used. Well, I used as an example on Monday. The reason why I've used this polygon is it's a concave polygon. By concave, I mean if I draw a line between 2 points in this polygon, let's say there's a point here and a point over here. If I draw a line between those 2 points, the line crosses over the edges of the polygon. So that means it's concave. If I couldn't do that, it would mean it's convex. Okay. So concave means there's a little sort of, somewhere in it there's a little dent or a little divot or something. Okay, so the reason why I'm using a concave polygon is that's quite difficult to do. In graphics, we normally prefer convex, but the Scanline algorithm can deal with concave. Okay, so let's say I've got a scan line which is there. Okay, so this scan line is at this point here, so this is represented by the dashed line. So I've gone down to here. Okay, I then go through each edges of this polygon. So the edge V1 to V2, okay, it's clear, but that does not intersect with that dashed line. So I'll check that edge, and then I'll go to V2 to V3. Okay, that's clear, that doesn't intersect. And I'll go for a few more. Okay, around the polygon, all these don't intersect, so don't have to do anything until I get to V6 to V7. So vertex 6 to 7 does intersect with the scan line. So what I do is I calculate the x coordinate of that point and call it x1. Okay, the y coordinate is dead easy to calculate. You just simply 1 minus whatever the y coordinate of the previous scan line was. The x coordinate we have to interpolate. So let's say I've interpolated that. So I have x1. Okay, keep going. V7 to V8, that doesn't cross the scan line. And finally, V8 back to the start, V1. Okay, that does intersect with the scan line. So what I do is I call that point x2. Okay, so there's my scan extrema at x1. That's my other scan extrema at x2. And I'm finished because I've gone all the way around that polygon. What I then do is x1 is greater than x2. Okay, so all I do is sort them in order, so that will mean swapping these two around. Okay, so if I swap them around, this now becomes x1, and that now becomes x2. And then all I have to do is render every pixel between those two scan extremes. Okay, and that's that scan line done. Move the scan line down and do the whole thing all over again. Okay, so now the scan line, I've moved it further down. Okay, so this time we do the same thing. Okay, V1 and V2 does not intersect with the scan line, so we move on to V2 to V3. As we can see, that does. Okay, so again, interpolate between excuse me, between V2 and V3. That gives us X1. Okay, so each time you move your scan extremer down, clear your X array or your scan extremer array, and then because each time they're going to be different. V3 to V4, okay, so that doesn't cross the scan line, but V4 to V5 does, and that intersects at X2. Okay, 5 to 6, as we can see, doesn't, but because this is a convex polygon, okay, we're going to have more than two scan extremer, so V6 to V7 does intersect. So I call that X3. 7 to 8 doesn't. Okay, so that's fine. But 8 back to 1 does. Okay, so in going around this, when I move the scan line down and going around this time, I have 4 scan extremer. You will have, you should have an even number of scan extremer. Sometimes a point or 2 scan extremer will exist, have the same coordinates, but you still have an even number. Okay, so we have 1, 2, 3, and 4. Okay, so the next step is we sort these into ascending order. Okay, so if we sort them into ascending order, then I have 1, 2, and 3, 4. And then all I do is I illuminate all pixels between 1 and 2. That's my first pair. Okay, I don't illuminate any pixels between 2 and 3, but I then do it again between 3 and 4. So you can see it can deal with convex polygons. So polygons where you do have a little sort of dent or a little hole sort of cut out of it. It's just what you tell it to do. So I'll show you the MATLAB code in a sec. So yeah, yeah, that's something you have to program in. You say, okay, fill between each pair. How do we calculate those x values of the x coordinate? Well, we use what we call linear interpolation. Okay, so on the right, okay, here we've got one end or one vertex of a polygon edge. I called it xi, yi, and we've got another end, and I called it xj, yj. So just two, that's just any edge of a polygon. And this dashed horizontal line is obviously the scan extremer. We need to calculate this point here, x and y. Okay, well, Cartesian equation of a straight line, y equals gradient times x plus the constant where in the y-intersect, where the line crosses the y-axis. So if we know what xi, yi is, and we do, because it's just one of the vertices, the constant, the value c, which is the y-intercept, you just rearrange this, insert xi and yi, and we have the value of c. So if we substitute this back into the Cartesian equation of a line, we end up with this. Okay, so this is a linear interpolation expression. So this is our x value. So this is our scan extremer. This is this value here. Okay, xi is this value down here. We could have used xj, by the way. I just used xi. So you can choose any end vertex. Plus delta x over delta y. So delta x is the difference in the x direction between the vertices of that edge, and delta y is the distance between the horizontal coordinates of the vertices of the edge. This is multiplied by y minus yi. So this y is here. That is known to us because at the start of the algorithm, our y would be the top point on the polygon, and each subsequent scan line we just subtract 1 from y. So y is easy to calculate. We just subtract 1 from it. Then we can calculate x using that expression, just simple linear interpolation. Okay, so coordinates of the scan extreme are, as I mentioned, y equals y minus 1. X equals xi plus delta x over delta y, y minus yi. Now, delta x over delta y is constant. Okay, it's a straight line. The gradient on any point on the straight line is going to be the same. So rather than calculating delta x and delta y for each step and for each scan extrema, we pre-calculate it. Okay, so we pre-calculate your gradients. I called them the gradients, but it's actually 1 over the gradient. But we pre-calculate that first, so we don't have to bother doing it for each step. We do have a problem if your edge is horizontal. If your edge is horizontal, delta y is 0, and delta x over delta y would therefore be undefined. So we do have to have a check. If delta y is non-zero, we calculate. If it is 0, we just set it to 0 because it's not going to be used. Okay, so that just avoids any sort of MATLAB throwing a hissy fit, really. Okay, so I've got a bit of MATLAB code here for you. This is just a function. The input is raster. So your current raster array, we've been using this for a couple of weeks now, so you should know that's a nx by ny by 3 array. P are just points, or your vertices. I should have called them V, really. And color is your fill color. First thing we need to do, and this goes for any form of rasterization, is if you're dealing with rasterization, we need to convert your screen space coordinates, which are in the range -1 to 1, to pixel coordinates, which would be in the range 1 to how many pixels you have in each direction on your horizontal and vertical direction. To do that, okay, so I've used the size command. So this size command just calculates, okay, what's the size of nx? So that's the number of rows in raster. That's the number of columns. So one thing we have to remember is MATLAB deals with matrix indexing. Okay, if we're looking at Cartesian, so if we're looking at x is our horizontal direction, it's always the second dimension in the matrix. Y is our vertical direction, so that's the first dimension in the matrix. Okay, and then what we do is to convert screen space coordinates to raster coordinates. Remember, screen space coordinates are in the range -1 to 1. So if I add 1 to my screen space coordinates, it's then in the range 0 to 2. Divide it by 2, I'm in the range 0 to 1. Multiply it by nx, I'm in the range 0 to nx. So this, everything after this comma here, whatever p is, or p1 is, the x coordinate, that will be in the range 0 to nx. But I haven't got a 0th pixel. Okay, pixels are natural numbers. You can only have discrete sort of whole pixels. So this max 1 ensures that if this number here is 0, we're actually saying, okay, it's the first pixel. And similar for the y pixel coordinate. Okay, so that's the first thing we're going to do. Convert your screen space to your pixel coordinates. Next thing we do is we pre-calculate the gradients. I've called the gradient dx in this code. So just whatever the change in x is. Okay, so n vertices, okay, how many vertices have I got in my polygon? And the one we looked at is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there's 8 edges in our example polygon. Set j to be the last vertex. So j would start off with 8, and loop through I for 1 to 8. Okay, and I calculate the slope. So got less than 1. That should be not equal to 0. Actually, Yeah, so that wouldn't work for all cases. There's a slight error in the program there, but okay. So if it was equal to 0, you set the gradient to be 0. Else, the change in the x coordinates for the vertices divided by the change in the y coordinates for the vertices. This update j at the end just means, so we start, j starts at 8 and I is 1. So we check between edge 8 to 1. And then j becomes 1 and then I is 2. So then it checks edge 1 to 2. So j is always 1 minus whatever I is. Okay, that's the first bit. So that pre-calculates the slopes. So notice dx will be an array. So each edge of the polygon will have a value for dx. Okay, and then you do the actual main algorithm. So from y equals top to bottom, okay, so top is just the maximum value of the maximum vertex in the y direction, to bottom, and this -1 in the middle just means increment down. Okay, so top will be a larger number than bottom. So every time we go down 1, okay, we're incrementing by -1. Okay, so loop through the polygon edges, determine whether scanline intersects current edge. Well, that's just logic. So this states that if the y coordinate of vertex I is greater than the scan line, and the y coordinate of vertex j is less than the scan line. So if one's above and one's below, or if it's the other way around. So this is if I is above and j is below, or it could be but I is below and j is above. So it's just using ampersand is logical and these vertical lines are logical or. N scan x is my way of saying how many scan extrema points have we got. So I start them off as 0. If I have a time when the scan does intersect, I just add 1 to it. Okay. And scan x is just the x coordinate of the scan extrema, and this is the interpolation. So it's xi plus that slope for the edge I multiplied by y minus yi. So that's just our interpolation equation. Okay, once we've done that for each edge, sort it. So the scan extrema is just the x coordinates. So use the MATLAB sort function to sort it in ascending order. And then this is the bit which is, where we ensure we're filling in it between pairs of pixels. So what I have here is a for loop that goes from I is 1 in increments of 2. So this will go 1, 3, 5, 7, etc. So this will go at all the odd numbers up to scan x minus 1. So its number of scan x is 4, this will go 1 and 3. If n scan x is 6, it'll go 1, 3, 5. Okay, and then I've got another for loop that just goes between each pair of scan extrema. Notice I've got a floor function here just to round it to a integer. That rounds down to the integer below. Okay, so that's the MATLAB code. So fairly involved. I mean, it's not something I get you to do in your assignment, but it's a yeah, that's the MATLAB code, and this is the result. Okay, so this is the same polygon we looked at before, but this is using that MATLAB code. The useful thing about this is it can deal with this convex region. Okay, it's quite difficult to do that, but because, and the reason why it can deal with it is because we sort the scan extrema in ascending order. Okay, one thing I did have a bit of a play with is when doing this is I've animated the flood fill and the scanline filling methods. So this is something I did, I don't know, yeah, hopefully it's up there. Come on, YouTube. Okay, so this sort of gives you more of an intuition about what's going on with the flood fill and the. Okay, so that was starting. This is a LIFO flood fill. So starting at a pixel in the middle. Every time a pixel is rendered, I'm plotting it to the animation. So you can see it sort of traces around everywhere and it doesn't leave any holes. Obviously, you never see this when it does it in practice. It's done instantly, but okay. So that was the Scanline fill. Sorry, flood fill. I just do that again. So the first pixel was this one here, and yeah, this one's a queuing base. This is a LIFO queue base one. So, yes, yeah, that's a good point. The flood fill requires an outline. Okay, so hence you can see the black pixels here. The Scanline doesn't bother with an outline. So if you did want an outline, you'd have to use your line drawing methods to draw it. And this is the same thing, exactly the same one. Ooh, does it too quick, I'm afraid. So that does it. Well, I don't know. Should have slowed that down. But as you can see, what the hell's that? Yeah, so you can see. Starts at the top, starts at the top, ends at the bottom, and yeah, you're right. It doesn't require, it doesn't have any outline. If you did want an outline, you just use Brescian's algorithm to draw the outline. Yeah. Okay, so that's filling. Advantages, disadvantages: much faster than flood fill. Okay, flood fill does one pixel at a time, and then moves to the next pixel, does that one, moves to the next one. Scanline filling uses what we call scan coherence. Okay, what's the point in doing one pixel at a time when we could do whole rows of pixels? We don't need the polygon plotted beforehand, so we don't actually plot polygons using Brescian's algorithm. We actually plot them using Scanline algorithm. Yeah, I mentioned scan coherence. Doesn't have to check every pixel, just has to check what are the edge pixels, the scan extremer. And we will use this when we look at lighting models, which will be next lecture at 11. We'll start to do with lighting and texture mapping, which is comes a couple of weeks, well, maybe week after next. Okay. Right, so I said it was quite a sort of short, little easy method today. Are there any questions on that? You can use it, but the outline would just be the same color as the fill color. No, you wouldn't. If let's say we wanted this, let's say we wanted to draw this, and you want to use flood fill, draw the outline in red, and your target color would be white. So remember, you got target replacement. You only fill in a pixel if it's a target color. So you'd have a red outline, and then you'd only fill it if the pixel's white. So if you wanted the flood fill but the same color as the outline, yeah. Another thing about this is I mentioned it can't be used to draw circles. That's actually a lie. It can be used to draw circles. Your scan extremer is just you calculate the edge of the circle. So if you do want to draw a circle, you can use the Scanline filling method. Okay, any questions on that? Yeah. I mean, I've sort of ended sort of after half hour. I don't want to change. I haven't got any questions on any of the assignments? No. Right. I think, unless you want me to go. Oh, I was going to say we'll leave lighting for the one at 11 o'clock. Okay, so I think we'll finish up there then and let you have a coffee. You just dragged yourself in. Yeah, my apologies for finishing so early. It's not a lot I could really say about Scanline. I have. Oh, that's good. It'll take you about 5 minutes of signing.